In this talk, I will talk about learning with arbitrary adversarial test examples, and this is joint work with Shafi Goldwasser, Adam Tauman-Kalai, and Omar Montaser. Okay, so the focus of this talk is in the task of classification, where we're given n labeled training examples, xi and f of xi, where the training example comes from some distribution p, and our goal is to learn a function f hat that is close to the real function f with respect to the distribution p. We emphasize that in this classical classification problem, it is assumed that the training data and the test data come from the same distribution p. In this talk, we diverge from this classical setting and consider the more general setting where the test distribution may be different from the trained distribution. This is indeed the situation in many real-world scenarios. For example, it was demonstrated that various commercial gender classification schemes that were trained mainly on light-skinned people do quite poorly on dark-skinned people. Sometimes the test examples are simply adversarially chosen. For example, adversaries generate offensive videos with the goal of fooling the filters in place. In this talk, I'm going to show you how to get rid of these adversarial people. We present a learning algorithm for learning an arbitrary concept class of bounded VC dimension for any test distribution. Previously, such result was not known even for learning intervals or learning half spaces. There have been two main lines of related works. The first considers the case where each test example is an adversarial perturbation of a trained example, and the second considers the covariate shift setting, which assumes that the test distribution is a distortion of the trained distribution. Both these works place some assumption on the test distribution. In this work, we consider an arbitrary test distribution, even adversarially chosen, even by a so-called white box adversary. Jumping ahead, we note that our work is mostly related to the work on selective classification originated by Chow. So let us illustrate the issues that arise in our setting where the tests and trained distributions are different via the example of learning half spaces. So in this classical problem, we're given a bunch of labeled examples, and we find kind of the best half space that fits this data. We predict everything on the left as positive, everything on the right as negative. And indeed, if the train and test distributions were the same, this prediction would do quite well. In this talk, we focus on the setting where the test distribution is different from the train and can be adversarially chosen. Unfortunately, it is impossible to predict well in this setting. Consider, for example, the case where the test distribution is focused on the top center. We have no idea how to predict it, since the real f can be this dotted line, in which case the predictions should be all negative, or it can be this dotted line, in which case the predictions should be all positive. So what do we do when we hit a wall? Well, we relax the model. And in this case, we allow the learner to abstain and predict question mark if he does not know the answer. Now, when given labeled training examples, the learner will predict only where he knows, which in this case is in the green and red ovals, and will abstain everywhere else, say in the gray areas. And now, looking at the example we had before, we can see he will indeed abstain in the oval on the top middle, which he should since he indeed does not know the answers. But still, there's a problem. The adversary can still fool the learner to predict incorrectly. And the problem stems from the fact that the prediction is never perfect. And it's enough that it predicts incorrectly on a single element, and the adversary will focus all the test examples exactly on that element. So let's look back at the example of videos, offensive videos. Suppose this F is the correct classification. What the adversary can do, he can place all his test examples exactly in the little oval in the red region, which will be predicted incorrectly as non-offensive, even though they are actually offensive. So what do? We relax the model even further. In addition to allowing the learner to abstain, we also give the learner test examples. Intuitively, this allows him to distinguish adversarial test examples from train examples. In the example above, the learner is given samples from this cluster of test examples, and thus will suspect this cluster as adversarial and reject it. Still, the question is asked, is this reasonable to assume that the learner has access to test examples? In some cases, the answer is yes. For example, in the transductive model, which we indeed consider in this work. But even if not, the learner can be adaptive in retrospect. And in the offensive video example, he can in retrospect delete these videos. We provide a learning algorithm, which we call rejectron, since it rejects or abstains to predict on some of the examples. This algorithm generates its best prediction on the labeled training data and also generates a rejection set R corresponding to the examples on which it abstains. Intuitively, R contains elements that the algorithm does not know how to predict on, or that it suspects are adversarial. So one can ask, what guarantees can we hope for? It is tempting to hope to guarantee a low rejection rate and low error rate on Q. However, this is clearly impossible, since Q can be very far from P, in which case the learner really has no information about how to predict the labels on Q, and he should actually abstain with high probability. Instead, we guarantee low rejection on P and low error on Q, which seems to be the right guarantee for this setting. More specifically, we prove that the rejection rate on P plus the error rate on Q is at most square root the VC dimension divided by N. We call this PQ learning, and note that it generalizes PAC learning, which considers the case where P is equal to Q. The guarantee of PAC learning is similar, but without the square root. Unfortunately, we show that this square root is tight and necessary up to logarithmic factors. So how does our algorithm work? The first thing it does is it finds the best function f hat in the class that agrees with all the training data. It predicts positive on the green region and negative on the red region. Then it computes the rejection set R. For this, it uses his given test examples. What the algorithm does is it finds some function C in the class that agrees with f hat on all the train examples, but disagrees with many, say epsilon n, of the test examples for some constant epsilon. It then rejects all the examples on which f hat and C disagree. So this is the gray region. Then it repeats this iteratively. It finds yet another function, C prime in the family, that agrees with f hat on the train and disagrees with at least epsilon n of the remaining, namely unrejected test, and rejects again the region on which C prime and f hat disagrees, and so on. Importantly, we show that our algorithm, or the computation of R, of the rejection set R, can be done efficiently given oracle access to the ERM, namely the empirical risk minimization algorithm, applied to C. So far, we show generalization bounds in the supervised and realizable setting. For the case where the test distribution is arbitrary, supervised refers to the case where the training examples are labeled, and realizable refers to the case that these labels are consistent with some function in the family. In our paper, we consider various extensions. In particular, we consider the transductive setting, the unsupervised setting, and the agnostic setting. Unfortunately, I don't have time to tell you about these today, but I refer you to the paper for details. So in conclusion, in this work, we construct a selective classification algorithm with low rejection and low error guarantees for arbitrary test distributions. And previously, guarantees were given only under some assumptions, either assuming the test distribution is a perturbation or a distortion of the train distribution. We emphasize that our results are incomparable to these, since these do not reject and we do. And in particular, our algorithm may reject perturbed examples if they are noticeably different from the train examples. Thank you very much.
Hi, today I'm going to talk about how to estimate the performance of any model under distribution shifts. The motivation for this work is very simple, that very often we use machine learning in high-stakes applications, but when we actually use our models in practice, the data that we see at deployment time is very different from the data that we actually trained our model on. So the question becomes, can we still trust our model? Is there some way to estimate how well the model would still do under this shift of distributions? The setup we look at here is the following, that we have data from a source domain where we actually have labels, and that's what we just use to train our model in the standard way. So now we have that model, and when we deploy it, we actually deploy it on a target domain where we don't have labels. So that could be, for example, a change of seasons where suddenly we have snow in the pictures. How could we estimate the target error or target risk? So generally what we do to estimate the performance of a classifier is that we just look at labeled data from the same source, and we just compute the test error, which is an empirical estimate of the risk, meaning the expected error. So what about the target domain? In the target domain, we don't actually have labels. So what could we do instead? Well, one simple idea would be, well, just use some other model to generate labels that are an estimate of the target labels. But how good is that actually? So let's just estimate the target risk by some labels that we get from a proxy model. Obviously, how well that works depends actually on how well the proxy model works. So we can formalize this by a bound that includes that proxy risk that we are going to compute. So basically the disagreement of our model with that proxy model, plus a term that's essentially the bias of the class of proxy models that we use. So basically, how well does the best model in that class actually fit the target data? To optimize that, we could just use a very rich model class that includes good models. And in fact, if the green term is small, then the blue term that we can estimate is actually a very good bound on the target risk. But there's one caveat to that the actual quality of our estimator also depends on how rich that class of target models actually is. So basically, the error is bounded by the worst performing model in that proxy class. To get sort of the best of both worlds and get a class of proxy models that is hopefully going to perform well, we use domain adaptation models. Because domain adaptation models are exactly designed for this setting, that we get data from a source domain that has labels, and we actually want to perform well on a target domain that doesn't have labels. As domain adaptation models, we use domain-invariant representations. The idea of domain-invariant representations is that you map the source and the target data together into some joint latent space, and then we train a classifier based from that latent space. So the way this is typically implemented in practice is both of them are actually part of a neural network, and the first part of the network is the encoder or the embedding, and the second part is the classifier. Now we expect that this actually works if the model manages to find a good alignment in that latent space and a good classifier. So the way we typically train this is that we minimize a combination of source error, because that's where we can measure error, plus an alignment of the source and target data in that latent space, so a divergence measure. And when would we actually expect this to generalize well on the target domain? Well, again, as I said, if the model actually is able to manage to find a good alignment, and second, as in any generalization bound, if the complexity of the model class is not too rich, so that we don't overfit either the alignment or the classification. So that's essentially what you get also formally. Now you may say, well, many of these generalization bounds, they are actually a bit questionable for neural networks, because we know that neural networks, if you increase the depth, the generalization actually still works quite well. And this is exactly what you observe when you look at the supervised task. So now here we look at just the source error, so the data from the source domain, measuring source error from our domain adaptation model, and we see that actually as we change the model complexity, meaning the depth of the network, nothing changes much. But the situation is a little bit different if you actually look at domain adaptation itself. So if you look at the target error, what we see is that the situation is different. So here I have two plots, one for the predictor complexity, meaning the classifier complexity, and one for the complexity of the embedding. And you see that while for the predictor itself also doesn't have much of an influence in terms of complexity, the embedding actually has a big influence. So if the embedding model is too complex, then we overfit the alignment and target generalization doesn't work anymore. So here actually complexity control is very important as opposed to the supervised part and the predictor. And the way we achieve this is that we actually do model selection here via the same idea of having a proxy model. So we actually show that you can self-tune the model. Putting it all together, the way we estimate the target risk is that we get a class of proxy models, and these are domain-invariant representation models that help us label the target domain. And then you just use those labels as a proxy for the actual labels. So this works because via self-tuning, we are actually able to select a class of good domain-invariant representation models. And the actual proxy class that we use is just a subclass of these models that has low cost as measured by the typical domain-invariant representation cost, meaning source error plus alignment. So at the end of the day, we optimize the proxy risk by optimizing with that constraint of having a good domain adaptation cost. How does this actually perform in practice? So here we see some example results where on the x-axis we have the estimated risk, on the y-axis we have the true target risk. And ideally we'd like the 45-degree line, and we see that actually we get very, very close to that. And we observe similar plots on different data sets. So how does it compare to the literature? There's other approaches that use an earlier bound by Ben David et al. That doesn't explicitly take into account the embedding complexity and doesn't explicitly do the proxy models. And you see actually it heavily overestimates the risk. And another approach based on confidence scores heavily underestimates the risk. So in summary, what we obtain is a very robust estimate of the risk of any given classification model. All we need is labels from that model. And as a side effect, we get new insights for domain adaptation about how the complexity of the embedding actually plays a role for domain adaptation.
Hi everyone, my name is Hadi. Today I'm going to tell you about how adversarial robustness affects transfer learning. Okay? This work is part of the MIT MSR collaboration. So transfer learning is a very popular, simple, and efficient way to obtain highly performant models on tasks where we do not have enough data or compute. Okay? So in a typical transfer learning setting, we are given some pre-trained model trained on some large-scale data sets, such as ImageNet, for example. And we're given some small target data set on which training from scratch is not sufficient to obtain good models. Okay. The goal of transfer learning is to leverage the knowledge or the good features or knowledge learned on a large-scale data set to obtain models that are that perform well on the target data set. Okay, to efficiently obtain models that perform well on the target data set. Right. So how do we do transfer in practice? There are two common ways for transfer learning. The first one is the fixed feature transfer learning setting. In this setting, we're given some large-scale dataset, in this case ImageNet. But what we do is that we train a model that achieves high accuracy on the ImageNet validation set. Okay? Now, given the target dataset of interest, to which we would like to transfer the knowledge that we learned on ImageNet, what we do is that we copy the pre-trained ImageNet model, we copy the whole model except for the last layer, and we freeze the parameters of this model. Okay? Then we stack a linear classifier on top of this model, and we train this classifier on the target dataset. So essentially what we are doing is that we are extracting some features from the target dataset using the pre-trained ImageNet model, and we are fitting a linear classifier on top of these features. Okay? And again, the hope is that by leveraging the high accuracy ImageNet pre-trained model, we get models that achieve high accuracy in the target dataset. And indeed, this is what happens. By following this procedure, we get models that are we get high accuracy and fast training on the target dataset. Okay. So this setting works fine in practice, but not as good as the other transfer learning setting, which is the full network transfer learning. In this setting, everything flows exactly the same as before, except for the fact that when we copy the pre-trained ImageNet model, we do not freeze any of its parameters, okay? Instead, we fine-tune the full model on the target dataset, and this leads to even higher accuracies and still very fast training, okay? So transfer learning is great and very practical. The question is, how can we improve it? So prior work and conventional wisdom have shown that in order to get better transfer performance, one shall improve the performance of the pre-trained models on the source datasets. For example, Cornbreath et al. Showed that better ImageNet models transfer better on a wide variety of downstream tasks. Okay, so but like, is accuracy really the only way to judge how well our pre-trained model transfer to downstream tasks? Well, one common perspective of transfer learning is that it's all about learning and transferring good features from the source dataset to the target dataset. But like, what is a good feature even? Well, deep learning is also all about introducing or encoding priors into our model during training into our models, which we believe improves the features that our models learn. Such priors include, for example, the architectures we use, the loss functions we use, or even the data augmentation techniques that we incorporate during training. Okay, in this work, we consider yet another prior, which is the adversarial robustness prior, and we investigate whether it leads or induces features that are useful for transfer learning or not. Okay, so the adversarial robustness prior basically constrains the model to be robust to small perturbations of its input, small imperceptible perturbations specifically of its input. So for example, given two data points x and x prime that are visually similar, this prior forces the model to output similar predictions for both of these data points, okay? And very recently, Angstrom et al. Have shown that like by using this prior, we get qualitatively different representations than the representations that we get from just doing standard training. And these representations, as shown in the figure, are more human aligned, tends to be more human aligned. So the question is, are these representations any useful for transfer learning? Before delving into answering this question, let's see how we can actually incorporate the adversarial robustness prior in practice. Okay, so shown on the screen is a standard machine learning pipeline for training ImageNet. So we have ImageNet, we have some model, we train ImageNet on this model, and we are able to achieve very high models that have very high accuracy on the validation set of ImageNet. This is standard. In general, these models tend to be brittle and not robust, specifically not robust to what's called adversarial examples, which are like small perturbations of ImageNet data points that lead to drastic changes in the predictions of the model. Okay, adversarial robustness is all about pushing the model to be robust to such adversarial examples. Okay, and this is done by many ways, and one of the ways to do this is using one way to do this is using adversarial training. The technique is very, very simple. Instead of training a model on ImageNet or the clean data points of ImageNet, what we do is that we generate adversarial examples continuously for ImageNet, and we train on those examples, okay, instead of training on the original dataset. And this leads to models that have high robustness to such examples, but that are characterized to have lower accuracy than the previous standard trained models, okay? So the question here is, does the adversarial robustness prior still help transfer learning, although there is a drop in the accuracy as compared to standard trained models? And the answer turns out to be yes. In order to validate this, basically, we train 4 different architectures on ImageNet, both with and without the adversarial robustness prior, and we transfer those models or those trained models into 12 different image classification tasks. And the figure that I show on the screen is one of the tasks, which is the Caltech 101 image classification task. And clearly the figure shows that the robust models outperform their standard counterparts on the transfer performance to this specific dataset. And very similar results hold for the rest of the 11 other image classification tasks that we consider. Okay. More interestingly, we find that the benefits from using adversarial robust models hold for other computer vision applications. For example, object detection and instance segmentation, both for which we find that for which we observe consistent performance boosts by using when we use robust models instead of standard trained models. Okay. So in addition to all of these performance boosts that we see on the various downstream tasks that I just showed, we try to delve deeper and try to understand what characteristics of the adversarially robust models that makes them good for transfer learning. Okay, and here I'm gonna show 4 of our findings very, very quickly due to the interest of time. So the first thing that we find is that for pre-trained models, both robustness and accuracy are important indicators of how well these pre-trained models transfer to downstream tasks. Okay. The other thing that we find is that if we increase the width of a standard trained model, we hurt transfer learning. Whereas if we increase the width of a robust trained model, we improve transfer learning, which is something very interesting, I find. We also find that the optimal robustness level for transferring to a specific dataset, so as to a specific target dataset, highly depends on the scale of that target dataset. Okay, and finally, we demonstrate that the robust models or adversarially robust models transfer better than texture invariant models to a wide range of downstream tasks. Okay, so in short, adversarial robustness seems to be a very good prior for transfer learning. And the interplay that we observe between the adversarial robustness prior and other priors seems to be nuanced and therefore requires further investigation. And once again, adversarial robustness have shown that it's useful. It's very, very useful beyond security applications in machine learning, which is a fact that I personally find super exciting for the field, and I'm very excited to investigate it more in the future as well. So by this, I'm going to conclude my talk. Thank you very much for watching, and I hope you have a great day. Thanks.
Hello, everyone. My name is Pouya, and I'm a first-year PhD student at MIT. Today, I'm going to talk to you about making online reinforcement learning safe in computer systems. There has been a significant and growing amount of interest in designing decision-making systems that operate with the help of learned principles. The complexity of these systems and the difficulty of coming up with solutions that can work well across a wide variety of environments has motivated people to use machine learning. It promises to learn an optimal behavior for any complex system. Applications of these systems range from video streaming, scheduling job clusters, task device placement in machine learning, and query optimization in databases. However, most of these learning-based systems are currently not safe to deploy. They're trained offline, either through a simulation or replaying traces in a smaller representative infrastructure. The models these systems use haven't seen all dynamics that usually occur in real-world examples. This matter cannot be fixed with more offline training data, and so these models fail to generalize the usual variations that exist in practical systems. These variations occur for a number of reasons, like new hardware, software, a new workload profile, etc. So, our goal in this project is to develop learning-based systems that can be trained in situ on a live production system. We employ online learning to achieve this. To ensure safety in online learning, we took an approach inspired by how humans learn difficult tasks. A small child cannot ride a bike like a professional from day one, and will likely fall and maybe hate bicycles forever. Put training wheels on that bike, and not only will the child learn how to ride it and build confidence, but also learn it so well that maybe it can one day ride it without the training wheels, and maybe even become professional. The system we propose works much like a vanilla reinforcement learning setting, where an agent picks an action, receives a reward, and makes better choices through evaluating its experience. The components that we add monitor the safety of the environment. Take the helm when things go bad. When in unsafe territory, a fallback policy reverses the system to safer regions, and learning goes on. If the system was safe in the beginning, it is the agent that will pick an action, receive a reward, and update itself with a new experience, like a normal reinforcement learning setting. To evaluate our ideas, we use a simple load balancing proxy environment. Here, we have a proxy receiving jobs and distributing them among several worker servers. The proxy doesn't know the size of incoming jobs or when the next one will come. It will assign each job to a worker and send back the results. However, there are two problems here. First, workers can freeze and delay the jobs assigned to them, or maybe even crash and render them incomplete. Second, some systems tend to have a mixture of small and large requests. Sometimes, small jobs are assigned to a server with a large request in the queue in front of them. This will cause a huge unnecessary queuing delay for the small job, probably much bigger than the job processing time itself. To fix these issues, the proxy also sets a timeout for that job, so that if it hasn't finished by that time, it can duplicate those requests on another server. This is called proactive replication or hedging, and is usually tuned to improve tail latency, like the 90th or 99th percentile latency. And the choice of this timeout is what we aim to learn with an RL agent. I should mention that the optimal rate of hedging depends on the workload the system faces. Let's look at this trace from a Microsoft service. What you see here is the rate of requests coming to the proxy. You can observe how there are different regions with varying load levels, from short intervals with peak load to light load regions that span several hours. Each region and load level requires a different strategy in hedging. The peak loads have a little budget for hedging, as they might overload the system, while in light load regions, the system can pay the cost of excessive duplication. But there is a problem here. Once the learner passes from one region to another and stays there for a long while, it might forget the right choices for the previous region. This is called catastrophic forgetting, and is a major issue with continual learning. Our approach to solving this issue is based on using multiple experts, each responsible for a specific workload. And we make the assumption that we can tell different workloads apart by some features, like the rate of requests. We maintain an expert for each different workload we have observed so far. Each expert has a model trained specifically to be optimal for that workload, and keeps track of the history of workloads it has handled so far. We'll call this the expertise set of that expert. We accumulate features over time and compare them to the expertise set of each expert. If there is a match, the model is updated with the new data, and we switch to using that model. New features are added to the expertise set so that they can be used for subsequent periods. But there will come times when the workload doesn't fit with any of our previous experts. So in these rare moments, we launch a new expert with a new model. A good starting point for the model will speed up its training. So we'll intuitively use the model of the expert that resembled that workload the most. Then we train it with new experiences, and now it will handle workloads of this new type. A well-designed multiple expert system will create new experts exactly as many times as necessary. Too many experts will mean less training time on average and less performance. Too few models lead to a model that isn't optimal on the workloads it presents, since it is representing multiple diverse, different workloads. So the way our system works is it will observe the state and features of the system, compare these to the expertise set of the experts that are available, and either pick an expert that resembles it closely or make a new one. Let me show you how these assignments look on a real trace. The blue line is the number of requests per second, like you saw a few slides back. And the thick lines represent the average number of requests our experts have seen. Look at the orange expert at the start, which keeps being selected until the load spike at the 3rd hour. A new green expert is created to handle this workload and is called upon again with further spikes. The process goes on until a 3rd model is created by the end of the day. As the process is automated, it will launch a new purple model on the same trace in the 2nd day. But as time goes on, the experts stabilize in their region and no new experts are necessary. Finally, let me show you the end results of this approach. Here we have the 95th percentile latencies plotted for 4 different baselines. The multiple experts continual learning approach, our approach, the blue, an offline learner trained on the first 2 hours of data, in orange, an online learner updated with every experience that it gets, in green, and a conservative agent that doesn't hedge at all, in red. The system goes through many different stages of load, with different amounts of delay. Let's look at a light load region in the middle. The multiple expert learner achieves 2 times better latency compared to other baselines. Let me show you why. The plot you see on the top right is the average timeout index of the agents, basically the actions they took, where a lower value means a shorter timeout and more aggressive hedging. The reason the multiple experts works better is because it detects the changes and uses a new model, which is specific to this workload. Other baselines don't perform very well because the offline learner uses the same conservative policy it had learned on a medium load. The online learner doesn't realize the workload changed until several hours had passed in the region. The online learner makes the same mistake again on the next few days, which demonstrates the catastrophic forgetting problem very well. Now, let's zoom in on a peak load spike zone. Our system handles the spikes better, and it gets more better as it grabs more data and further learns the characteristics. It isn't quite as great as the conservative agent since it needs time to train, and the spike duration is short. In conclusion, machine learning has the potential to revolutionize the delicate process of designing systems, but only if we overcome several important challenges. Our approach here is making online training safe with training wheels, while making it robust and quick to adapt via multiple experts learning. We aim to create a reliable platform for deploying learning-based systems in production. Right now, we're working on controlling exfiltration during workload changes to further improve performance. That marks the end of my presentation. Thank you for your time.
Hi everyone, my name is Cathy and I want to first thank the organizers for this event and the innovative format. Today I will be sharing an update on our work on policy transfer across networks towards understanding AI impacts in urban systems. In order to have trustworthy AI systems, we must be able to assess their impacts on the systems in which they operate. Automated vehicles gradually introduced into existing urban systems is such an example of this problem. A guiding question in my recent work is whether deep reinforcement learning can help here, for instance, in analyzing the potential impact on traffic of automating a fraction of vehicles. We can cast the problem into the framework of reinforcement learning by considering the agent to be the fraction of vehicles that are automated and considering the environment to be everything else, including the human drivers and the infrastructure. The agent will make decisions such as when to accelerate or change lanes according to a policy denoted by pi in order to maximize the reward. We are concerned with global rewards, such as the average velocity of all vehicles in the system. In our work, we will use policy gradient methods, in particular TRPO and PPO. The goal is to find a good theta which parameterizes the policy such that the expected cumulative reward is maximized. Following the milestone results that demonstrate the potential of deep RL in the domains of video games, board games, and locomotion, we would like to take a step towards societal systems. Switching our attention now to the environment, we use an open source traffic microsimulator called Sumo. Traffic microsimulators are actually used to plan cities. They are among a rich class of urban simulators and their defining characteristic is that they simulate each individual vehicle in the system, which is microscopic in the grand scheme of whole cities. One of the basic behaviors of an individual vehicle is called car following, which dictates how vehicles accelerate in response to its distance or relative velocity to the vehicle in front of it. A popular model describing this kind of behavior is called the intelligent driver model, which is given by this differential equation and is what we use in our work. It might look complicated, but the models are actually designed to be quite interpretable and are calibrated to real driving data. But this is only the most basic of behaviors. These models need to be supplemented with much more involved driver behaviors, such as fail-safe logic, merging, lane changing, and so on. Behaviors that cannot be as easily written as differential equations. These behaviors in turn must be coupled with important simulation elements such as road networks, roadway signage, and so on. Although it is quite common in RL research to skip the details on the environment, here I want to point out that a striking feature of traffic is that no two cities are the same. It is possible that not even any two city blocks are the same. This can potentially limit the ability of RL to analyze the impacts of AI. If given every new part of a road network, we always need to train from scratch. This is why we are interested in transfer learning. In previous work, we have shown what is achievable when training from scratch in each new environment using existing RL methods and with modest compute. We designed a representative set of small scenarios that exhibit a variety of traffic phenomenon. Using RL to learn policies for 5 to 10% of vehicles in the system, we see a 30 to 140% improvement in average velocity across the scenarios, and this has near-term implications for automated vehicles. In the course of our study, we found that some of the learned policies actually match the behavior of control strategies devised by experts over the years. Other learned strategies exceed previous control strategies and achieve near optimal performance while eliminating traffic jams. These findings provide validation for the methodology of employing RL to analyze the impact of AI in urban systems. Now, in order to study larger and more complex scenarios, we are interested in where knowledge can be transferred across traffic scenarios to understand whether this is a promising direction to improve the sample efficiency of RL on these tasks. We refer to transfer learning as the use of knowledge gained from a source task to bias the learning process on a target task towards a good set of hypotheses. More specifically, zero-shot transfer is the extreme setting where no learning is done on the target task. It is analogous to out-of-distribution generalization in supervised learning. We start by examining situations where we intuitively expect transfer to be successful. One of the simplest possible traffic scenarios is a single-lane circular track, and the performance upper and lower bounds on the average velocity can be characterized by computing the system equilibria of the corresponding dynamical system, which we can see in this figure, for a range of traffic densities in the x-axis. We also give the state-of-the-art controller by Stern et al., which is a hand-designed proportional integral controller with saturation, which we can see performs better in lower traffic densities and worse in higher traffic situations. Now we take the white range of densities in the middle and call this our training regime, or our source tasks. And we take the gray densities in the outside to be our testing regime, or the target tasks. Our learned controller achieves near optimal performance. It's perhaps not surprising that some amount of transfer should be successful, since the network and underlying dynamics are quite similar. What's surprising here is that the zero-shot transfer actually retains near optimal performance. One of the common criticisms of the circular track is that it does not have any bearing to reality, since most traffic systems in the real world are open networks. In collaboration with Abudi at Berkeley, this motivated us to assess whether, from a learning process standpoint, there is similarity. That is, whether knowledge can be transferred between closed and open networks. There are a few substantial differences between open and closed networks, which I won't get into here, but the consequence of this is that in the open net road, in order to have an interesting traffic problem, we need to introduce a merge point to introduce perturbations into the system. Then we find that directly transferring the policy learned in the closed system to the open system already yields average velocities higher than human driving. The performance can then be fine-tuned from there. This experiment provides evidence that knowledge from closed networks, which are most of our early experiments, can be transferred to open networks. Finally, in ongoing work led by Z and my research group, we are studying the potential for a single policy to transfer to many different scenarios. Here we study a traffic bottleneck, which is characteristic of many highway networks. An interesting aspect of traffic bottlenecks is called a capacity drop. If we take a look at a diagram which shows the relationship between the inflow of vehicles to the system and the outflow of the system, a capacity drop is characterized by, at first, a linear relationship, which is what we expect. And then instead of leveling off at the capacity of the bottleneck, we instead first see a drop and then a leveling off. When we employ RL to learn a policy for 10% of automated vehicles in the system, we are able to avoid this capacity drop and increase the throughput. And we see this interesting behavior emerge where automated vehicles take turns holding strings of human vehicles back, which avoids contention at the bottleneck. We now treat this as our single source task, and we find that the policy transfers well to different bottlenecks with different numbers of lanes and segments. We also find that this transfers well to different fractions of automated vehicles. For instance, here we see a graceful degradation of the performance to the capacity drop as we decrease the fraction of vehicles. We then take this same policy and transfer it to a very different network, one that currently we are not able to train from scratch, which is this 3x3 grid network. Taking a look at the intersection highlighted in the red circle, we can see that the behavior from the automated vehicles is reminiscent of the bottleneck. We can see the red vehicles switching off, holding back strings of vehicles. The result of this zero-shot transfer experiment is an improvement of 26% in throughput over the human baseline with no fine-tuning.